and then they'll be pointing to my site, right? I mean, I'm paying $21 for a click to sell home equity loans. That's two domains. I can register 2 domains with that, maybe even 3 with certain domains. Maybe it's like $7. Is it $7 for a domain now? I don't even know how much it is per domain. So, sort of the new trick is, here's how I, make my site look good. I'm some not so nice site on the web. I sit there somewhere in the web and I have some content, or I'm selling something, and no one links to me. I'm just sitting there bored and lonely. What do? Well, I mean, first I create some pages. I add in some extra nodes in this graph. Then I link to myself. So I'm now going to make all of these pages and these new friends that I've created, I'm going to make them link to me. They're all going to link to my page. So now suddenly I look very popular. This may look a little fishy to a search engine, so I say, okay, well, how about I have them link to each other as well? So all these sites have now linked to each other. It looks like there's this big, complicated network which is surrounded by me. They're all linking to me. Look how popular I am. I'm a really, really good web page. Now this still looks a little fishy, so maybe what I do is I also say, okay, well, you know what? I'll just have them link to some other normal pages as well. I'll create some other pages, have them link to some good pages as well. Right now, if you're an indexer and you didn't see the evil faces, this might look like a normal web graph, and might look like a very popular page. So this is basically what web spam is. I think that you don't actually have to create your own domains now. I think there's actually businesses which do this for you, and they have pages which look good and which have links. You basically pay them to put links in different places. But I think this is basically the way it started. People would just generate new domains, or they would take other domains and start putting pages that looked like good pages. I just got one of these, I think. Let me see if I can do this easily. Yeah. Oh, is this going to... where is it? Yeah, this is a spam page. You guys probably saw spam. I think a few years ago you saw a lot of web spam. I haven't seen it in a while. It was actually very hard to find. No one links to web spam anymore. You can't, the Google searches don't come up with web spam anymore. I even typed in spam examples. You couldn't even find them. Turns out one way to get your site to drop in PageRank is to link to a spam page, because it looks very, very fishy. So I guess if you look, basically, there's all these random, here if you want to go to hotels, and all it says is, we show you the best selection of websites and hotels, and it just has all these random links to other sites, and flights, and again, best selection of websites and flights and holidays. All these pages are exactly the same except for the word in bold here. So we'll have to get back to where is it? Oh. Did it work? Oh, that's good. So in terms of a learning problem, this isn't typical. I mean, you actually have adversarially generated. You have a graph with adversarially generated nodes. I mean, web pages that were created for the sake of fooling you. I mean, most machine learning problems are ones where there's some kind of, you assume there's some random process generating your data. Trying to figure out, maybe there's one process generating one type of data and one other process generating another type of data. Like maybe you're trying to classify, standard machine learning problem, maybe classifying cancers or classifying people's faces and images. That's a standard machine learning problem, But you sort of assume this is generated by some natural process, like for example, people's genes creating the way that their faces look, and the environment. This is not a natural process. This is a process created for the sake of fooling you. I mean, the point is that you didn't want the indexer to actually be able to figure out which pages are spam. So I mean, it's interesting. I mean, you have this hyperlink graph as well, but it's not clear what the hyperlink graph means. I mean, what does a link mean? I mean, I have a link, and I know it goes somewhere, but what does it mean? Was it created for the sake of, this page actually thought that this other page was good, or did this link mean that, that it wants to boost the rank of this page, or is this link just meant to, this particular host is just used as a spam host, but it's just linking to good, it could be linking to good hosts just for the sake of making it look like it's not a bad host. I mean, it's not clear what's going on. There's a lot of confusion now in this problem, right? So from a machine learning perspective, this is sort of what the problem looks like. You have a big graph, and this, think of this as like millions and millions and millions of pages, and then you have a few that that are bad, and a few more that that are good. In fact, in general, I think roughly 10% of pages are bad. So there should be like a 10 to 1 ratio here. And then you have all these hosts in the middle, and you have no idea. And of course, you can't label them, by a human. You can't, it's too expensive to label all these nodes. But you want to say, okay, I have a very sparse collection of good nodes, an even smaller collection of bad nodes. Now I want to figure out, what about these guys in the middle? Are they spam or are they not spam? How can I trust the links coming from their pages? So it turns out that there's one observation here that is very, very important. I don't know if you guys have ever worked on web spam, you probably know what this is. One fact about web spam, which is basically consistent across the board. Can anyone guess? has to do with the links. So it turns out you almost never see a good page linking to a bad page. It almost never happens. So basically, if you see a host that you're sure is good linking to another host that you don't know, you can almost be certain that that host is good. I mean, it's not certain, but you have a really, really strong guarantee that's page. You know this page is good. You've looked at it. It looks like a good page. It's literally like CNN.com. CNN.com is not going to link to a spam page. That's a huge advantage. That sometimes makes the problem very easy in some sense because there's basically you can be pretty sure that nodes that basically only have links that go to bad pages and or links that only have links that come from bad pages are going to be no wait, hold on, sorry, I just get confused. Links that what was that? Oh, someone walking by. Sorry, I thought someone asked a question. You know that when a good page links somewhere, you can almost be sure that the other page is good. And that's a very, very nice fact. That makes the problem much easier. So basically what I'm saying here is that you have a good node like this, you're never going to see it linking to a bad node. It's never going to happen. That's very, very helpful for you. So if you saw a node in here linking to a bad node, that would also tell you a lot as well. It's very likely to not be a good node. So I'm going to talk about some sort of methods that have been around for a while for detecting web spam. There's sort of roughly two categories. One is graph-based, the other one is content-based. One you sort of try to take advantage of the hyperlink graph. You try to use the hyperlink graph as much as possible. And the other method, you try to use the content of the pages. So the graph-based methods are sort of very similar to sort of PageRank. You guys most of you guys know what PageRank is or have a rough idea what PageRank is. TrustRank is basically, it's roughly the same thing. It uses sort of some different, its sort of parameters are different than the PageRank algorithm. Typically with PageRank, what you're doing is you have these are sort of your ranks, your ranking numbers, or your scores for the page. It's some vector of scores t. The capital T is a transition matrix, so it's basically just the matrix generated by the links. So if the ijth entry is 1 over the number of outgoing links from the ith. If there's a link from I to j, you put 1 over the number of outgoing. It's normalized. You normalize by the number of outgoing links. So it should be a probability matrix. And basically to compute PageRank, you sort of hit this vector t enough times with this matrix capital T, and then of course you're supposed to sort of add kind of like a constant factor of alpha every time to make sure that everybody gets a little bit of trust or a little bit of PageRank, and then after that it sort of propagates from there. I don't want to go into too much details with this, but this is basically roughly the PageRank algorithm. But with TrustRank, what you do is you set the initial distribution to be basically you set zeros for pages that you don't know anything about, and you set 1 over m for the pages that you are sure are good. So you have pages that you're sure that are good, and you make the initial distribution 1 over m, where m is the number of good pages that you know about. So effectively, you have your initial distribution start with only good pages, and all the bad pages get zeros. In fact, yeah, for this algorithm, you're not even using the bad nodes. If you have some bad nodes, you don't actually take advantage of them here. And there's actually methods for taking advantage of bad nodes. I can ask me for that after the talk, and I can shed some light on that. So basically, in the end, the trust scores it's what's going to come out of the algorithm. In the end, you're going to hit t, little t with this matrix capital T. It's going to be something like the stationary distribution of this Markov chain. That's a whole other field. I don't want to get into that now, but trust rank, basically, you can actually think of it as sort of a random walk, where basically you're starting in the graph at a good node, and you just start walking. So here we're just going to start at that node right there, and you're just going to start walking around the graph. And basically, if you run this for a number of times, where are you going to end up? And if you end up at a given node a lot of times, it means it's probably not spam. And this is sort of a good heuristic, actually, for checking if something's spam, because if you could get from this node from a good node, then probably this guy linked to a good node, he probably linked to a good node, he probably linked to a good node, and then at the end, the last guy should have been a good node. Nodes like this guy right here, that's a bad example, actually. Nodes like this guy right here are probably not good nodes, right? Because he's only linked to from bad nodes, and he only links inside the graph. Basically, the only incoming links he has are from bad nodes. So the other class of methods are called content-based methods, and basically you just look at the page. You try to analyze, have I seen this page before in the web, or how many words does it have, how many links does it have, can I compress the page, is it really, really easy to compress, maybe there's really no information on the page. And you basically try to train a classifier, maybe just a linear classifier or some kind of, take whatever off-the-shelf fancy machine learning algorithm you have and just try to train it on some features of the page. Take the page and just, boil it down to some important features that should help you find figure out if it's spam or not. And this is sort of standard machine learning approach, just training a classifier on some features, standard trick. Here you're not using any of you're not really using the hyperlink graph. Maybe you'll use the hyperlinks to generate some other features. Maybe you'll say like, how many outgoing links you have, that'll be a feature. But roughly this is basically you're taking advantage of the structure of the graph, the topology of the graph. So what the algorithm that I worked on is called which, or we called it which. We sort of chose which sort of at midnight on the submission deadline because we couldn't think of anything better. But it basically, the letters work out correctly if you write which. So we wanted to take advantage of both content and hyperlinks. So we wanted to have web spam identification through both content and hyperlinks. We wanted to use both the link information and the content of the pages. And both of them are valuable to some extent, but we want to be able to use both of them. So the kind of key ingredients of this algorithm, I'm going to just give you a sort of an overview right now, is that we sort of use a sort of standard support vector machine framework. This is kind of the kernel method, finding a linear classifier. Support vector machines are good because they're efficient. I don't know, you may not know about SVMs. It's not, I'm not going to go into too much detail about the sort of mathematics, but it's sort of an efficient method. You're basically finding a hyperplane in some kind of high-dimensional space to separate your data. It reduces to some optimization problem. It always reduces to an optimization problem, which generally can be solved efficiently. So we had to add these slack variables, which is sort of, I'm going to try to describe that later. What is a slack variable? And this is a very, very important feature of the algorithm. We use what's called, or we're calling semi-directed graph regularization. Graph regularization is sort of a new trick that people have been using in the machine learning world. If you happen to have some data points and you also have some relations between the data points, so you have two different types of inputs. You have both the features for a data point, like the contents of a page, but you're also given some kind of relationship structure, like a graph structure on your data. You can take advantage of the graph in the regularization procedure. Now, if you don't know what regularization is, it's not just such a big deal. I'll give you kind of a rough idea of what it is in a second. But graph regularization lets you kind of train a classifier, train some kind of a decision function, which should vary sort of smoothly along the graph. It shouldn't change. If node A links to node B, then there shouldn't be that much difference between the predicted values between the two nodes. So the last thing that I was sort of just writing a final slide about, and I don't have much, if you guys should ask about this later if you're interested in this, is the optimization procedure was basically some sort of Newton-like optimization. I don't know if you care about that. If you care about it, ask me about it afterwards. I'll probably sort of gloss over the optimization trick. This is very important, of course, for large scale. Like for what people at Google do, this is very important. The optimization, because we were all working on sort of data sets that fit within one computer, and if you're working on a data set that really doesn't, has to fit on like a distributed hard drive, that's these kinds of questions are how do you optimize functions? That's a big question. So standard SVM framework. Is there a laser pointer? It doesn't matter. If you can find one. So standard SVM, standard support vector machine. What you do is you basically minimize this cost function. So you're finding some vector w. So xi is your data point. You have L data points here, and xi is your data point, and you minimize basically how well your vector w classified. See, yi is your label. This is going to be it's +1 if the page was spam and -1 if the page was not spam. You want w.xi to match the sign of yi. So this number is basically going to be 0. This sub plus means it's hinge loss. Don't worry too much about this function. This is basically saying how well this term says how well did w classify x? How well did w classify x? And it's just hinge function. If you got it right, if you're way off, it starts to increase. And in machine learning, you learn about these things. It's not too crucial. The point is, this says how well did you classify the data point? This term says how big was the vector w? So when you minimize this function, you want to say I want to minimize the error I made in my training set, plus some regularization term. And the regularization term is basically saying how complicated is your classifier. You don't want to have a complicated classifier. You want your decision function to be sort of simple. You want it to kind of be smooth. This is sort of a general theme in learning. When you're learning, you have to control complexity so that you don't overfit. It's basically an overfitting control. If you make sure that your classifier is smooth, that ensures that you won't overfit your data. So the graph regularized SVM is basically like the standard SVM, but you add in a second term. Second term is this graph regularization term. What you're doing here is you're saying I want to fit my data well. I want to have a symbol classifier, but I also don't want my function to vary much along the graph. Here, E is my set of edges. No good? OK. E is my set of edges, and I'm going to look at all pairs of nodes. I and j are 2 nodes. And I want to make sure that my classification function, w.xi, is not very far away from w.xj. I'm not sure that's clear. So what's happening here is this is the predicted value of node I, and this is the predicted value of node j. And if I penalize for the square difference, this is maybe like an edge weight, some kind of an edge weight. If I penalize for the difference squared, that just ensures that this is saying that I want my classifier to not change. If A links to B, I don't want w.xi, or if I links to j, I don't want w.xi to be very far away from w.xj. So I'm going to penalize for the difference. For those of you who don't know about this regularization, this is the key idea of this part of the algorithm. The last thing is going to be the slack variables. So it turns out that you can't get good performance if you just train on a standard linear classifier. You need to actually say, I'm not only going to learn the spamicity of a given node by training a linear classifier, w times the features, which is a dot product between some weight vector and the features. That's what w is. It's the classifier. I'm actually going to have to learn some zi for every node. So zi is some value, some predicted value for every node. And I have to actually throw that into my algorithm. So my final output, when I predict the spamicity for a node I, the final output is going to be w.xi, which is like, what are the features telling me? And zi says, OK, what do I actually just think about this node? Let's say based on maybe where it lies in the graph. So you're learning w.xi plus zi. That's the actual final output. That's what you're predicting as the value on each node. And again, you're going to regularize for the w, and you have to regularize the z's. It's very important you regularize both of these things. And in the end of the day, you also graph regularize these predicted values across the graph. So I'm going to regularize the predicted values along the graph. This is the predicted value for node j. This is the predicted value for node I. And I sum this up over all ij in the graph. So this is graph regularization. It's a support vector machine with graph regularization. So yeah, the terms. These are the terms. The new additional terms. So it turns out that this I was using this square difference. So I'm predicting. I'm trying to predict whether all these things are spam nodes or not, and I want it to be smooth along the graph. The graph regularization says that if I don't think that spam nodes should link to non-spam nodes. But it turns out that if you just use standard graph regularization, it doesn't actually take into account the directionality. Right? I said the directionality is very, very important. It's a very, very crucial factor in how you learn these things. So standard undirected graph regularization, like I had written before, what I had over here, this is just the difference squared. Difference squared, there's no directionality, right? That's just, if they're different, I penalize. What I should have is something that tells me actually more, well, what happens if a bad links to good, that's okay, that sort of seems natural, right? I said that it's, they might do that to try to fool the indexer. But if good links to bad, that's a very bad thing, right? I really don't want that. So an alternative is directed regularization, where I do something which is kind of like a hinge squared, you can call it. What's happening is that if it's not going to be SA minus S, this is if SA is the predicted spam value of node A and SB is predicted spam value of node B, and A links to B, it's going to be like, it's not going to be this thing squared, it's going to be like the minimum of this thing and 0 squared. So you sort of draw, if this thing is negative, you just say it's 0. I don't know if I got, maybe it should be positive, maybe I got the direction wrong, but you see what I'm saying? Like if A is greater than B, then you penalize for the difference squared, but if B is greater than A, you don't penalize. That's fine. If the spam linking to non-spam, that's okay. Spam linking to non-spam is not a problem. We don't want to penalize for that. So intuitively, you would think that this would be much better because it does have this directionality, right? The directionality is very, very important in the problem. Turns out this was actually false. We discovered. Here's a graph of performance of our algorithm. I'm not going to talk about sort of the algorithm and general performance and metrics and stuff in a little bit, but high means good and low means bad. We're measuring AUC, which is area under the ROC curve. It doesn't matter if you don't know what that is. It's basically saying how well did you rank the pages? How well was your ranking of spamicity? Turns out that on the left side is directed regularization, and on the right side is undirected regularization. This is what I was initially suggesting, and I'm saying shouldn't be correct. But then I said let's try to change it and use directed regularization. Turns out that direct regularization is much worse than undirected regularization. But a little bit of undirected regularization and mostly directed regularization is actually the best thing to do. You can see I'm actually mixing the two here. So I'm actually considering what happens if I consider, I can think of a trade-off. I use either one or use the other, or I just use kind of a mix of the two. I can say, alpha of one regularization plus 1 minus alpha of another regularization. That's what this alpha parameter is. Saying, let's say use a trade-off between the two. Turns out that this very, very minor trade-off, if I just use a little bit of undirected regularization, that's the optimal thing to do. That's the ideal thing to do. And this is really surprising. We actually didn't figure this out until right at the end. And this seems to be a very, 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 very crucial part of the algorithm. The reason why we have gotten such good performance is because of this fact right here. So it turns out this sort of semi-directed regularization looks like this. It's not quite a full quadratic. It's not quite a quadratic on one side and then flat on the other. It's this kind of weird sort of lopsided quadratic where you don't penalize a lot over here and you penalize a lot of penalize a little bit over here, but not very much. Sorry. Penalize a lot over here and not very much over here. So this is, I think I used alpha equals to 0.2 here, but I think the optimal was alpha equals to 0.1, so it should actually be a little bit lower. I mean, it should be about down there. So we actually were curious with this. Why didn't this, why didn't our intuition that you should penalize for spam linking in one direction, just spam link in one direction? Why do you want to penalize a little bit in the other direction? Well, what's going on here? So we spent a lot of time looking at this, and it turns out there seems to be a lot of bad cases. The classic bad case is this one. You have a spam node, your short spam, it links to some node, and that node that you don't know the value of, this is the question mark node, links to good nodes. So spam node links to unknown node, links to 3 good nodes. So what do you do in this case? Well, if you're using undirected regularization, if you're just trying to basically pull the spam score only in the direction of sort of the, so what's going on? I get confused here all the time. So if he is said to be spam, that's perfectly consistent because spam links to spam, and spam also links to non-spam. There's no problem with that, right? If he is not spam, well, spam links to not spam. That's perfectly consistent. And not spam also links to not spam. That's perfectly consistent. You're not penalizing anything there. So in fact, this guy can have a value of anything, right? And there's a lot of uncertain cases where you just have no idea what to do. If you just use the simple one-directed regularization, this guy, his value is basically free to move, and I think his value just gets set to 0 because you don't have any idea what you just give him basically a default value. So a lot of guys were just getting a lot of sort of the uncertain cases were just getting sent to 0, and that's bad. You sort of want to say, well, in this case, look, he's linking to 3 good nodes and he's linked 2 from 1 bad node. I should if it was the opposite way, there's 3 bad nodes and 1 good node, I should probably think he's bad, but this way I should think he's good, right? There's something very crucial here. I mean, I actually do want to use the links to good guys and the links from bad guys a little bit. I should use them a little bit for sort of the cases where I can't make a decision, right? This is sort of the hardest case. And here I think the algorithm, what it's going to do is say this guy is good. It's going to predict he's good, or it's going to give him more of a goodness score than a badness score. Because he has more outgoing friends that are good than incoming friends that are bad. Yeah. So, I just wrote this slide up like sort of half-assedly when I was finishing this. So I thought maybe people would be interested in this. The optimization was sort of Newton step style. Basically, we haven't tried this on large data sets. We've only tried this on small data sets. But it is actually a pretty fast method. You have to do, in Newton method, the Newton optimization method, you have to do Newton steps, which require you to invert a Hessian. But you don't actually have to invert the Hessian. Hessian is this big matrix. Remember, you have tons of variables here, so you don't want to invert the Hessian. It turns out you can play games to get the Newton step if done efficiently. You can use linear conjugate gradient to do that. And that requires every time you want to do one Newton step, you have to do roughly 50 or 100 passes over the data, which is you'd have to look at your entire web graph and your entire feature set for all the pages 50 times for every single step. And you need about 10 steps. So you'd have to look at your data about 500 times to do this. And I mean, in terms of scalability, we don't know if those numbers scale correctly as you move up. Well, that's actually still kind of an open question for us. And that is a very important open question. So we, of course, we were interested in how well this thing works. This is sort of right now an inter-algorithmic comparison. I told you that if you add different features, first, the standard trick for classification is SVM, support vector machine. Just train a linear classifier. just try to see if you can put your data points in high dimensional space and just try to find some kind of a separation plane between your data points. Standard SVM trick. If you do that, you get the blue curve. This is, by the way, how much data you get, and this is the performance in terms of AUC, is how well you rank the data. So the blue curve is just train SVM, simple, first-year graduate school trick, or maybe even senior in college, or if I don't actually know how they teach these things in undergrad. Okay, now take that and now throw in graph regularization. Now try to find a linear classifier, but also penalize it for predicting across the graph, for sort of predicting wrongly, for changing along the graph very, very rapidly. You want it to be smooth along the graph. So the graph regularization sort of it'll. I wish I had a whiteboard. I could show you where there's a. Oh, I do have a whiteboard. You have graph regularization comes into play when you're finding a linear classifier. Oh, did I? Oh. And you have like two dig data clouds, like one here and one here. And you know that this guy is good, smiley face, and this guy is bad. And if you didn't, let's say you have like some graph. This guy's pointing to all these other nodes in here. You have some big complicated graph and some graph over here. Same thing. Oh, did I do this right? Oh no, sorry. It should be like sad face here and happy face up here. Yeah, up higher. Now, if you just sort of train a classifier without using kind of this unlabeled graph data that you have, you would probably do this, right? Or did I get it wrong? Maybe it's like that. Right, you would just try to separate these two data points, because you sort of don't see these. You're not using the graph at all, right? You just have two data points. You separate it like this. But if you use graph regularization, you also say that the classifier shouldn't cut through the graph too much. So actually you would choose something like this, right? Which is sort of the right thing, right? If I saw two data clouds and I had one data point per cloud, this guy's good and this guy's bad, I probably think that the rest of these guys are also bad. That's sort of the trick with graph regularization. So if you throw in graph regularization, you do get a slight performance, particularly when the number of labeled nodes is very, very small, which makes sense. When you have fewer and fewer labeled nodes, you do a lot better. The big boost seems to come from slack variables. You add those slack variables in, you get a huge improvement in performance. And that seems to be the following. It seems like you can't really, we only have like 200 features. And the features are basically like based on the content of the page, the links, the incoming links, the outgoing links. The features don't tell you enough, because people can spammers can just copy the pages from other pages, and they can just take pages that look good and make their own page out of them. So features don't really tell you enough to make a decision. These slack variables say, well, for each node, I can also learn a specific score, a specific spamicity score, independent of the features. And that freedom allows the algorithm to do a lot better. Now, of course, by doing that, you may overfit your solution, so you have to regularize those slack variables as well. There's a trade-off here. You give the algorithm more freedom, but at the same time, it might overfit. But it's still, nonetheless, those slack variables are very, very important in a procedure. You get a huge boost in performance from the slack variables. Now, if you just use slack variables and forget about features, ignore features, you get the red curve. And if you use everything together, slack variables, features, graph regularization, everything, you get the black curve. So that's the one. That's the algorithm that we're kind of I'm promoting here as we're calling which is that top curve. Now, it seems like the features don't help very much lower on. In fact, this shows that they hurt, but I don't believe those numbers. Sort of 1% of the data wasn't really enough data to check that. I think they do about the same right at the bottom. But features give you a pretty decent boost, not a major boost. The slack variables seem to do a lot more. So we took part in a web spam challenge, this summer. They had two tracks. They had a track where they gave you like the actual like websites themselves. They said, tell us if these are spam or not. Then they had a track 2, which is just they give you some hidden data set where you didn't get to see the actual, you didn't get to see what the actual pages looked like. You just got some features for the pages, and it was just a graph, no information about what the pages were. So we took part in this, and it turns out we actually won the second track of this, which is the only one we took part in. We tried again on the track 1 data set, and we actually would have won that if we took part in it. I'm only saying that to brag, but of course, in hindsight, of course, it's much easier to beat people once you've seen what the kind of the benchmark is. But we were actually a pretty hefty margin away from the leader. So on this particular competition, we actually did very well. And you can actually look at these are sort of I just showed you graphs of all these different sort of variations. Which is the bottom one. The challenge winner got 0.956 AUC on the track 1 data set, we got 0.963. And you can see we all seem to do pretty well with very little data, which I think is pretty cool. With 10% data, you still do quite well compared to the other methods. And that was also a big thing, because the data set was actually pretty well labeled. I mean, the number of actual labeled nodes in the full web graph is going to be much smaller than what we had. I mean, we had 10%. I think 10% of the nodes were labeled, which is not realistic. I think that's basically all I have to say. That went quicker than I expected it to. But feel free to ask questions, and thanks to Alexandra for putting those animations together. So.
What were the features that you used when you?
They were kind of, there was a variety. There was some content. So basically, they took, I think they did some kind of they checked some, they had some like SVD of the words in the page, some kind of SVD representation of the words in the page. They used also some kind of link-based features. They checked to see what was like the length of the words in the links. I think they may have also done like taken the words in the anchor tags, the anchor, what are they called? What's between the AHREF? What's in between there? It's called anchor. The anchors. They did some kind of low-dimensional feature representation of the anchor tags. They also said how many words were in each page. And it wasn't very complicated. The features were relatively simple. I think they had also some frequency vectors, if you know what those are. I can check. I mean, it's been a few months since I looked at that, but there was a variety of different features. I mean, they had a variety of different things they checked. Like how many links were coming in, how many links were going out. It's a freely available data set.
So in the graph that you showed, it seemed that on low percentages, features don't really matter. At least they're equal. You said that. How does that make sense? Well, even if the data is a little bit off, they're still pretty close together.
So let me go back. So you're saying that features are useless down here. Yeah, I mean, we have 200 features, and down here it's like you have like 200 labeled data points. So you have as many data points as features, and that's kind of like a situation where like it's very hard to really learn what's going on in terms of the feature representation. Still up here you have the entire graph. So if I still tell you that I have 10,000 nodes in a graph, but I can tell you what 100 of them are, you can still propagate pretty well the information from the graph. The graph is still very rich, right? The graph tells you tells you a lot. The features are sort of, I mean, as I said, the features are sort of useless, I think, unless you have a lot of features, unless you have a lot of data for good features. And they don't seem to help until basically you get up here. I mean, we're still improving as we get up here. That's the best answer I can give you. I don't really know. I mean, I think this comes from the adversarial nature of the problem. I mean, the features are the page contents are being created to look like they're good pages, unless a human actually looks at them and says, this is obviously trash, and this is obviously nonsense. Yeah, I mean, I think that basically the conclusion from here is that the graph tells you everything, right? The graph is so much more valuable than the features. The features give you a big boost right at the end there, but it's not clear if that's really, yeah.
So your assumption was that good pages almost never link to bad pages.
Well, I checked this. It does happen actually, but it's like.
It doesn't. Yeah. Well, unfortunately, it does happen. Does your algorithm tell you anything about these good pages that?
Yeah, we didn't. It's a good question actually. I mean, I actually checked this because I looked at the labeled set, and I think there may have been, in terms of, I looked at all the links between the labeled nodes. I think there may have been something like 5,000 links, and this is I'm getting roughly on the order. 5,000 links from bad pages to good pages, and maybe like 100 links from good pages to bad pages, or maybe 300 links from good pages to bad pages. So it was like a factor of 20 difference between the direction of the links. And I think honestly, my sense is if you ever link to a bad page, this algorithm would basically say you're spam, because that's just such powerful information. You can't ignore that information. You can't sort of say, well, maybe he made a mistake. That information tells you so much. If someone links to a bad page, it just tells you this person does not look trustworthy, right?
Yeah, but there are some cases where pages that have many good properties of good page still link with that page.
Yeah, I mean, I mean, I haven't. We don't require me to actually look at every single, page and see what the contents of the page and whether this guy just made a mistake or not. I don't know whether we were making a lot of errors. I don't know if maybe that was just maybe we were doing well because we were classifying a lot of pages as being bad. Maybe our algorithm was just too pessimistic. I mean, it's very possible. And I haven't looked closely enough to see, is this page, where were we making our mistakes? Was it because, these good pages just made mistakes and accidentally, did this link exchange and linked to a bad page? We didn't check that. I mean,
what I'm just asking is there a way to identify pages that their properties kind of varies? On one end, they get many good links from good pages, but their outlinks seems to be suspicious. So in a way, they're not trustworthy, but they are maybe good content.
I mean,
Is it coming out of some numbers?
I don't know. I haven't looked at the statistically. Asking an interesting question. I mean, I haven't looked at the statistics. I mean, that's the important thing to check. But it doesn't happen very much that good pages link to one page that you don't know, and then one page only links to bad pages. I mean, that never happens. Why would good pages link to a page that's linking to bad pages? I mean, it does seem counterintuitive. I mean, these things should happen very, very rarely. That's the hope. Realistically, these things should very rarely happen. Based on the assumptions that I'm making, that those things shouldn't happen very often, and the hope is that they don't. I mean, because I'm really using the direction of the links very, very, very heavily in the algorithm. So, I don't know if that answers your question, but
We can
sure. We'll chat about it afterwards. Sure.
Along the same line, if it does happen that a good page links to that page, any good page linking to that good page is kind of screwed. So, but at the same time, like if you had a labeled set of good pages and bad pages, maybe you could develop some sort of classifier for those kinds of pages, because that's not a situation where you have an adversary that's trying to make a good page link to that.
Explain again. What's the explain that again?
So if you had a labeled set of labels of pages where, as in if you could label a page as a good page that links to bad pages for node.
Oh, I see. Because it could be like you could be like because in some sense you could be like the indexer of the bad page, like a spam page, right? You're like a government agency which just indexes spam pages, right? I mean, then you're on a bad page, you're just sort of points says, hey, don't go to this site, right? I mean, you're right. I mean, you would imagine that should help performance, right? You would imagine that if you could say, don't trust that link. That link doesn't, But I mean, how would you learn that? How would you find out what links? That's another whole other learning problem, right? How do you find out what are the links that weren't intended to be?
Not learning problem. It seems like
That's true. Yeah. No, that's a good question. Like maybe you could do like another layer. Like first you train and see what links should be trusted. You find a weighting on the links, and then try to use that. Basically, you should maybe try to find the graph weights, and learn the weights in the graphs, and then do another, and then basically do something like this. Just try to train a classifier, so figuring out which pages are spam. That's actually a good idea, and it's a decent idea. And we didn't actually take advantage of we didn't play games with the weights too much. The weights for the edge weights are basically like log of the number of links from this page to that page, or log of the number of links from that host to that host, or log of 1 plus the number of links from that host to that host. We didn't play too many games with the weights, and we probably should have. I mean, the trust rank algorithm, they need to have a probability distribution on the outgoing weights. So like some of your outgoing weights should be equal to 1, and we didn't do that at all. I think we found it didn't work as well. We may have tried it once and it didn't work as well. So, anyway. Yeah.
And your problem configuration is kind of a very classic graph regularization kind. So a lot of work shows that the graph regularization can be interpreted into the Lady random work, which is kind of very like the test ranks.
Yeah, I wonder. I mean, we actually didn't say that. You're asking, was that your question? I don't know, because this directed graphic I was actually going to point this out, that it almost seems like if you use a little bit of sort of if you're penalizing a little bit for the links that go backwards and penalizing a lot for links that go forwards, it's almost like saying, with probability alpha you follow a positive link, and with probability 1 minus alpha you follow a backwards link. And that seems kind of natural. I mean, it seems like and I don't understand the random walk literature well enough to be able to say if that's what we're doing. I know that our algorithm is very different from that because when you train an algorithm like graph regularization with features, it's not clear. You can't simply say that training a regularized SVM, graph regularized SVM, is some kind of random walk because you have these features that are there. It's not just, you don't have just the nodes, you have features as well. It's almost like you would take a random walk, look at the features, make a decision, and then take walks to take a, I don't know how to interpret it in terms of lazy random walks. So.
I want to discuss this because I think your work is kind of has strong relation to trust rank. And another thing I noticed that is that select variables can help a lot.
A lot, yeah.
So the select variable can interpret as a page rank or a trust
Yeah. If you just use Slack variables, it would just be like trust rank. I mean, it wouldn't be exactly, but it'd be along the same lines as trust rank.
Indicates that the trust rank, your method is, is basically based majorly based on the trust rank algorithm and the feature things at little
I'm not sure. Trust rank doesn't use. I don't know if trust rank uses. My understanding was they don't use the bad nodes. They only use the good nodes. So goodness propagates forward. They don't have. So yeah, they have like GB. I think you've heard of GBU, the good, the bad, and the ugly. Some guys at Yahoo. They basically said you should do like a trust rank, which is like how much like trust propagates out of the good nodes, and then you should do an anti-trust rank, which is like how much should it propagate backwards. And I know that we beat them, but I think we tried that and we did better than that. But that still roughly sort of a similar idea. I mean, we might be doing something similar to that with some sort of you taking advantage of features as well. I mean, your point is well taken. It's a very good point. We can talk afterwards if you want as well about that. So. Yeah.
Just one sort of common thing to bring up. I don't know if it's really consumer comments. Comment spam is going to be a very common feature of most successful web spam, at least in the sun. Especially on older pages that don't have the kind of no follow tags and no links that most like modern blog software has. It's like, pretty common to find a guest book from, say 2000 or something that has like several thousand links to spam pages on it, where the overall site that links to this page that links to all this spam is basically good. It's just old.
I see.
And it's just people getting more savvy about kind of spam that's usually a lot and more of a problem in spammers.
I see. So you're saying that, yeah, I mean, the point is you should definitely not include comment links inside of your algorithm.
That's kind of a problem with the system itself, and it's hard to differentiate from.
Yeah, I imagine that's a good point, actually. Like, that seems like obviously it's a big problem. Comment spam is becoming so pervasive right now that I haven't played around with that kind of data, so I don't know. Any other questions?
Thank you.